And so you essentially close the circle and you can keep doing it. I like perpetual canon better for that. It makes more sense. The idea of the infinite canons is that you can slide these, the ones we were just doing, you could increase the delay between them in a continuous manner.
In a continuous manner.
So it's mostly the time aspect that is continuous.
Okay,
it's not that you do have to transpose the melody appropriately so that you have the right harmony.
Have you tried this with other tempered pitch sets? I think the other ones are 31. I can't remember what the...
I have not. I have not.
But it would be possible, I'm sure.
Oh, sure, it would be possible with any, yeah. Okay. And you can, I focused on consonant combinations just because that is sort of a proof of concept, right? You can hear that it works, but you could maintain a dissonant sonority as well.
Thank you. Okay, can we have the first question? I think the microphones. Anyone? I'm sure there are lots of them. Anyone? You've been so mathematically stunned. Come on, there must be at least a few. Yes. Is there a microphone?
This is to all speakers. Considering how much research we've done and what you're doing into maths and music and how it interlinks, do you think in the future we'll be using mostly computer programs or some sort of robots to create music?
Who would like?
Maybe I can say something about the use of computers in music, because at IRCAM actually there is really a trend of young composers really being excellent computer scientists also, and I think this changed a lot the way in which composition is conceived, in the sense that they can really explore a lot of dimensions, theoretical dimensions, which are not possible to explore without the modeling of this theoretical stuff into a computer-aided program. I mean, it's always possible to kind of do by hand, but for example, the things I was showing for these VUSA canons, you cannot obtain by hand. I mean, it's really you need algorithms. You need, and actually, the interesting point is where. Composers, they kind of understand things which are coming from the maths universe, but they kind of use in a personal way. They like this example by Fabien Levy or other composers. They are not just interested in taking a model and see what happens in music. So they want to kind of disturb this, kind of change the model and see if the compositional ideas they have, they can reach some theoretical mathematical statements or properties, but in a very personal way. So the surprise we have every day when we work with composers is that they come with for example, compositional ideas, then we show types of algorithm and process that I was showing, and then they go back to their compositional activities, and they kind of use in a personal way. Then when they come, we have the impression they put a lot of knowledge that was not there, and that's really a kind of very interesting collaboration. So otherwise, it's just pure maths applied to music, but this it's limited as an interest from a musical point of view. So this is my view.
Thank you. Would you like to respond to that?
There are at least two different kinds of things one can imagine. You could imagine, the computer actually basically just having their own musical life, writing the music, performing it, etc., for other computers. And on the other extreme, there is humans are still, it's still an activity of play and practice and performance and expression by humans for humans that the computers can help you with. I mean, that's sort of what happened. Chess isn't really a kind of either math or music, but it's happened in chess that computers can now beat you essentially with 100% probability. But humans are still playing differently against humans because we can practice with the computers, we can use the computers to analyze, we can use the computers to store data and so forth. I don't think the computers are going to reach the music that the point of being able to write, to sort of beat us at writing music unless we reach the singularity, in which case God knows what happens. Curiously, of course, that's popularized by Kurzweil, who became famous by creating musical synthesizers and so forth. But it's going to be an increasingly useful tool. I mean, I might be one of the last generation here who grew up and learned music without the computer. And so we are at this transitional time here when we have this new tool and we are still getting used to how to best adapt it to our human musical purposes.
Professor Callan?
Yeah, I might say, picking up on both of those sides, the work of David Cope in computer and music intelligence and experiments, where he would take music from, say, Chopin, mazurkas, and then the computer would sort of intelligently, but programmed to be so, recombine this, and then you have several mazurkas, 2 of them written by Chopin, 2 of them written by David Cope's program, and you have to decide, which is the computer and which is the composer. And I remember doing this test, a little bit skeptical of the project, and coming away a lot less skeptical because I didn't do as well as I thought. I mistook some of them. So that, I think that it poses a lot of interesting questions about music, that we could be moved by something that was essentially a recombination of previous work. The other side of that is, as a composer who works with these sorts of things, I really love the kind of hybrid nature of humans working with computers, achieving things that you couldn't do otherwise, but essentially using technology in a way that is kind of extends human capabilities, like we do with all sorts of things.
I mean, what you're describing, the way you're describing David Cope's work isn't really that far in principle for what a human composer does, right? I mean, just like we learn a language by recombining the sounds that we hear around us, and some composers do it more explicitly than others. I think there is the example of the same Mozart quartet that Beethoven recomposed twice. But even if it sounds like he's doing something completely new, most of it is, putting together something that's already, the musical culture is already, given you, and putting your own personal, orientation in it. But it's not all that far, I think. It's just that, it's very hard to teach a computer to do that, and that's amazing that Dave Cope can do it as well.
Yeah.
Thank you. Another question? Yes.
Hi. This is just about improvising canons. To what extent do you think someone can just carry on continuously improvising a canon like the one we heard today? For example, just if they just sat at the piano and they just carried on just improvising a canon, how long do you think they could go on for?
Well, I didn't have to stop when I did. If it's a short enough, if it's a short enough interval, like I could probably, I was going to say go more or less arbitrarily, but you won't want to hear an hour of canon any more than you want me to hear an hour of me improvising at a piano continuously in any case. There are written out canons that go on for the entire piece. There's a famous, should be more famous than it is, one by Bach, the second, what do they call him, duetto in F major? I don't know if you... But then you realize you come into the middle of this canon and suddenly... So he actually created this to be something that you could do in a canon in a very close scan like that, and you notice that he's reinterpreting this as a sequence. So once this works, and again, this would be the PDQ back version, but yeah, I mean, you don't want me to do this right now because we only have half an hour for questions, but I'll gladly, during the break, improvise the canon for much longer than I did before. You didn't want to hear that.
Thank you. I suspect most of us would like to hear you do it now. Okay, thank you. Another question, please. Yes, at the back, lady in the red gloves.
Okay, so this is actually about mathematical modeling of music composition. Of course, I'm very astounded and astonished by the role that math can play in musical composition. Sorry. But the thing is, right? When we usually associate the thing called modeling with a certain degree of rigidity, because we say, okay, if we are modeling something, we are actually putting some restriction onto it. So do you think this, the act of modeling music with mathematics will actually restrict to a certain extent the creativity of the musical conversation, or it will further extend the creativity? Thank you.
I think this is an answer from Elkham, isn't it?
For me?
Yeah, I think it's for you.
So
Okay.
what
Anyway, the others would like to answer.
What was exactly the question that I didn't get? So,
Whether
is the use of mathematics limiting the creativity?
Whether
Is that-
mathematical modeling would limit the creativity since you have restrictions.
Okay, that's very interesting question. I don't know how to answer. I think if mathematics is used in a kind of inspirational way, it cannot restrict the creativity because I think there are basically two ways of answering your question. If you have limited models of creativity, of mathematical creativity, then you are also limited in the way in which you can apply it to music. If the tools are kind of large enough and flexible enough to grasp creative processes, then I think you can really kind of broaden your compositional perspective with ideas which will not be possible to explore without mathematics. So this basically, I don't know if...
Thank you. Professor Callender and Elkis would
Yeah,
like to...
I would say, as one example, the various excerpts that Moreno played of composers using tiling canons. It's all the same mathematics underneath, but the way this is interpreted, the way it's realized, there's so many creative decisions that are made, so many more than the decisions or the aspects of the composition that are being modeled mathematically, that you get the composer's unique voice, you get their creativity. If someone, you could either have limited mathematical models, or you could stick so closely to the mathematical model and not think about creative ways of interpreting them, realizing them. That would also be a problem.
Professor Elkis?
I was reminded of the aphorism of Stravinsky, who said that it was when he was putting the most restraints on himself that he was feeling the most free. I mean, a blank sheet of music paper is completely unconstrained, and as soon as you start to write music, you are placing yourself under constraints, whether they come from mathematics or anywhere else. So it's certainly it's the nature of the constraints that plays that figures into what kind of music you will end up writing. But the mere fact of being constrained is a fact of the fact of compositional life, and it's a good fact of musical life, because otherwise you wouldn't be able to get started. Sorry.
Actually, yeah, I have also maybe a nice example to show you. If you are coming to the T concert today or tomorrow, where we are playing. Actually, I'm not a composer, contemporary composer, so to say, but I'm interested in pop music and the way in which mathematics can be applied in order to kind of open some compositional process in popular music. So I will show you how Hamiltonian paths in the tonets can be used in order to build Hamiltonian songs that you can appreciate maybe without knowing that it's really mathematically based, but I could never compose without the help of mathematics. So this is really a kind of example that I like to show, and is a song, so I mean, everything can enjoy without knowing the history of contemporary music.
I think one mustn't forget that music theory is full of constraints. I mean, it's a whole set. There's a pitch set, whether it's just or Pythagorean equal tempered. There are harmonic constraints or rules. There are contrapuntal constraints. So I think you don't need a computer to have constraints. They're built into the theory. And as Professor Elkis said, constraints can lead to more freedom and creativity, in fact. I think we had another question.
Yes, this has to do with the implementation of mathematics that you get from musical analysis into solving physical problems. Saying, for instance, we have Joseph Fourier that was studying the propagation of heat. Joseph Fourier.
Yeah.
Something more abstract that many people could think. Electromagnetism has nothing to do with music, say, for instance. Do you think in the future, because we are getting into a realm where mathematics and physics and music can all be joined together and so forth. What do you think about that in terms of joining these fields?
Okay, I'll ask all the three speakers.
don't
Who
know
wants
if
to start off?
You want to start?
I think you should start.
I have maybe an answer to your question. There are many ways in which music, mathematics, and physics can be put together in a very kind of surprising way. One of the examples I like to quote is the diatonic theory has been developed in the States, in the Buffalo School, for example, around John Clough and other doubted Norman Carey, David Clampett, and also in Europe in a parallel way. The diatonic scale is a very nice example of a space or a concept or a set which corresponds to what physicians call the Ising antiferromagnetic spin. Physicists call Ising antiferromagnetic spin plus minus 1/2 model. What does it mean? Ising model is just a way of putting, electronic charge, if you want, if you have the line and you want a stable system, there is no question. You put up spin, down spin, up spin, down spin, etc. But if you have a finite system, like, for example, a circular representation with boundary conditions. So a line with boundary condition makes a circular representation, and then you want to put electrons in such a way that the system is the most stable as possible, but you end up with the diatonic scale. And diatonic scale is really the way in which you can put 7 points around the circle in a most stable way, physically speaking, and also what we call in music theory maximal even sets in a maximal even possible way. And I think this is a very nice example, and actually Jack Doughty wrote articles in physics journals by starting with the theory of diatonic sets and exploring Ising antiferromagnetic model in a very original way. So I think the future is open to this kind of mixed collaborations between physicists, mathematicians, and music theorists. Maybe you have something to add to this.
Professor Kade?
I'll try. I'm not sure I have much to add to it. One thing that is interesting to me is that you don't need, compositionally speaking, you don't need a lot of math or physics or these kinds of things to come up with really interesting results. For instance, a logarithmic spiral or something is a pretty basic mathematical tool. A lot of the work in, say, the integers mod 12 produce a lot of very relevant and interesting mathematical, musical results. So that would be one thing. I guess I would say also it seems very natural that we will, like all other disciplines, we will continue to have a greater understanding of the structure that underlies the materials themselves, how we use them, well, I don't know what will happen with it, but it'd be nice to see.
Professor Elkis?
What is it? Hard to make predictions, especially about the future. There are all of these neat connections one can make, and the diatonic system is also that basic 12-beat scale. A pattern that we hear in some, not just in Africa, but in various drumming circles. But no pun intended. One has to be a bit careful, because not only can you. Yeah, it doesn't take very much mathematical content to give you interesting ideas in music. But music is one thing and math is another. If you try to have a complicated math formula and translate it directly into music without any musical intuition and communication involved, then, well,
And it's an exercise.
it's an exercise, and you don't want to hear it as music. And it's very tempting to try to bring back the classical quadrivium of what was it, geometry and astronomy and music, and what was the fourth one again?
Arithmetic.
Arithmetic. Thank you. But it's been a long way since the ancient Greeks and the Renaissance, and each one of these has gone in their in very well, math and physics somewhat in parallel directions, music in a rather different one, and yes, it helps to to have some sense of the common, of the common origin of all of them in human experience. But don't try to make music that's too explicitly mathematical or vice versa, because you have to keep your music musical and your physics related to the physical world and so forth.
So what you're saying is that ultimately music has its own internal consistency, logic, rationality, and all that.
And which we want to interpret, to investigate as its own thing, and physics, math, and many other things. Theater can be good inspirations, but we shouldn't expect we'd probably do better to expect our music to be theatrical than to be physical.
Okay, I think we can have one last question, because
We have this in the background. Wrap up.
Because we need to give you people time to eat before the concert, which is I think 1:15. So one more question. One more question.
I'm here. Sorry.
Yeah,
Okay.
it's there.
Yes.
This is for Professor Elkis. You
Where?
mentioned
There.
you mentioned A should work with B, because A comes first and then A goes to the bottom.
That's
and
right.
The second voice, you got to invent B that goes with A.
Right.
And you mentioned something about if A goes with B, then B should go with A.
Right.
Musically speaking,
Right.
how you distinguish the two, A tilde B and B tilde A? Mathematically, we often can conceive of them as different statements.
Yeah.
And we want to prove that they are the same in the way of showing equivalence relation, as you mentioned. But musically, how would you make sense of that?
Well, all it's saying is that if you have two voices and one of them is singing A at the same time that another one is singing B, then in almost any harmonic system that would be acceptable precisely when you switch the roles. There are some exceptions, like, clarinets make one kind of sound structure and violins make another, and so you can have an overtone of the clarinet clash with the violin if you have A with B, but not vice versa. But if you have two equivalent voices, I said it's almost axiomatic that it doesn't matter who's singing which part. So that's all I'm saying. It's a property of almost any reasonable, a property or an approximate property of almost any kind of harmonic system that you're going to be working with. Just like A almost always works with A. Okay.
When we say a motive A,
Yeah.
we actually mean a whole collection of sequence of notes, because you
correct.
can transpose them,
Yeah.
right? Now, if you transpose by one semitone, obviously it doesn't work.
That's not A, it's T1 of A.
Well, but then that's why I'm not very clear about what A is, Because to a beginner, A might just be a sequence of A, C, G, something.
You're right. I mean,
So it's almost like you're talking about A as a class of sequences.
No. When it came to the point of making sequences, I distinguished A from T2 of A from T4 of A, and it's not an axiom that A always works with T8 of A, let's say. Some transpositions always work, some transpositions never work, and some of them, I guess it depends on what your dogma is about fourths. But no, A is one thing, and A played in a different key is another thing. It's related by transformation that you can describe mathematically or musically, but you have to keep them separate.
Okay, regrettably, I think we should wrap up the session. Anything more from the speakers? Okay, then can we give all the three speakers usual round of applause? Thank you.
Thank you.